Section 5.2 is on area. Now this might seem a little out of context. It's not necessarily integration yet. It's definitely not derivatives yet, so it's not something like we've done, but what we're doing is going to set a stage to understand why do we care about antiderivatives. And one of the most useful applications of antiderivatives is to find the area beneath a curve. So the idea is geometry, and we learn this in elementary school, middle school, even in high school. We can find the area of certain shapes, triangles, rectangles, squares, circles. But what happens if a real-world shape, like most real-world shapes, aren't a perfect rectangle or aren't a perfect circle? How do we find the area of those? And what we'll find out soon is that to find the area of any shape, we can use antiderivatives. But before we're able to get there and draw those conclusions, we need to start finding the area of shapes using things that we know, like finding the area of rectangles, and break down shapes that we don't know, like a curve, into a bunch of different rectangles. So we're going to be adding a bunch of areas together. And when we want to add a bunch of things in mathematics, we use something called sigma notation. The sigma notation is this Greek letter sigma, being that giant E looking thing. And the idea is sigma here means sum or add. So we're going to be adding a bunch of areas together, and that's what we want to do. So when we're using this sigma notation, I want you to get used to it. I want you to see how limits tie to derivatives, tie to antiderivatives, and all of this ties to area. And that's what section 5.2 is about. Let's learn the notation, and let's draw things together to see how things work. So we're going to look at sigma notation, we're going to look at the area of a plane region, and then we're going to find the area by using the limit definition. So let's start off right here. It says the sum, for sigma notation, the sum of n terms, a1 through an, is written as the sum of I equals 1 to n of a sub I. So what you see here is you have two counters. On the bottom you have where you start, the number that you start at. On the top you have the number that you stop at. So you're going to count from 1, 2, 3, all the way till you reach the number n. And then each one of the terms is called a sub I. So what you do is you plug in a 1, and then you increment it. The sigma means you're going to add between each one of the terms. And each time you increment the counter I. So the first time you would have is a sub 1 plus, now increment I, a sub 2 plus, a sub 3, and you're going to keep on doing that all the way until you meet the upper limit, which is n. So it says where I is the index of the summation, a sub I is the ith term of the sum, the upper bound and the lower bounds are n and I. So n is the upper bound, 1 is the lower bound. So that should be n, and that should be a 1 right there. Okay? All right. So let's make sure you understand sigma notation and how to do it. So what's the idea? We are going to have from numbers 1 to 6 here, and all it says is plug it in, whatever that number is, I plug it in. So if we plugged in the first term, we'd have a 1 plus, because it's sigma notation, we add between them. We increment our I, then we'd have a 2 plus, 3 plus, 4 plus, and then it would be 5 plus, and then you would stop at the number 6. So that's what it would be. Let's look at this next one right here. What's the difference between these two? Well, I want you to notice that my increment starts at 0 now, and my upper limit's 5. But what are we going to do? We're going to take that I value, and we're going to add 1 each time. So if I plugged in 0, I'd have 0 plus 1, which is still 1, plus. And then it would be 1 plus 1, which is 2. 2 plus 1, which is 3. 3 plus 1, which is 4. 4 plus 1, which is 5. And then the last number we would plug in is 5. 5 plus 1, which is 6. So if you see, these two actually represent the same series. A series is where you just add a bunch of different terms. That's what we call a series. Okay? So both of these are the same series, but there is a difference between the series notation. The counters are different, and the I is a little bit different. Okay? You don't have to use I's, you can use any letters. So this next one, we're going to use J's. So anywhere we see the letter J, we're going to start by plugging in the number 3, and we're going to increment all the way up till we get for J equals 7. So what would we have at first? Well, we would have a 3 squared, then a 4 squared, then a 5 squared, a 6 squared, and we would go up to 7 squared. Of course, we could simplify it and find out what the sum is, but that's not what this is asking us to do. It's not saying evaluate the series, it's saying expand the series. So show us that you know what each of these terms look like. We don't need to actually evaluate it. Of course, we could put it in our calculator and do so. So let's look at this one. Start at plugging in j equals 1 all the way to 5. So what would this look like? I would have a 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4 plus 1 over the square root of 5. I stop at 5 and I'm done. Again, all I'm doing is expanding it, not actually evaluating it. How about the next one? This one's a little messed up. Let's see what this looks like. The reason that I'm saying this one's a little messed up is because here we have an n, so we don't know how many numbers we actually need to plug in. But what I want you to notice is a lot of people think you plug in for the n, and in this case you most definitely do not. You're plugging in for the number k. So what would we have here? The first term would look like 1 over n times, and then it would be 1 squared plus 1, right? What would the next one look like? Well, it would be 1 over n. Remember, we are not plugging in for n. It would be 2 squared plus 1. Then 1 over n times 3 squared plus 1. And we would continue this all the way. I'm going to put dot, 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 the ellipses, meaning continue the pattern, until we reached n. So this would be 1 over n times n squared plus 1. Okay. All right. Let's look at the next one. It says, find the sum I equals 1 to n of f of x sub I delta x. So what would that look like? Wherever you see an I, plug in the number 1 and then keep on going in. So this would be f of x sub 1 delta x. That's where I saw an I. Sorry, I don't need an equal sign there. I need a plus sign. That's where I saw an I, so that's where I plugged in the number. Plus f of x sub 2 delta x. Plus f of x sub 3 delta x plus, and we would continue that pattern until we reach the number n. So this would be f of x sub n delta x. So that's what that would look like in expanded form. Again, I don't even know how many terms that is because they haven't specified what n is. All right? Okay. So let's look at Theorem 5.2. These are summations that I expect you to have memorized, or minimally, if you're allowed a note card, on your note card. But these are the ones that I want you to memorize. The sum of a constant. So let's think about it like a constant like 5. So you'd have 5 plus 5 plus 5 plus 5 plus 5, and you'd do that n times. So 5 plus 5 plus 5 n times would be c times n. Here's the sum was I equals 1 to n of I. It's n times n plus 1 all over 2. There's a really, really cool proof of that one. I don't want to get into it right now because these videos are already long enough, but there's a really cool proof of that one. It came from a young mathematician in middle school who was asked to add the first 100 numbers, so from 1 to 100. He counted them forward, he counted them backwards, and then he divided it by 2. It was really, really cool how he arranged it and how he did it. Look into it if you're interested. The sum of the first I squared terms would be n times n plus 1 times 2n plus 1 all over 6. This one would be the sum of the first I cubed terms would turn into n squared plus times n plus 1 squared all over 4. So we are going to use every single one of these. You do need to know these formulas. Now what I want to call these is I like calling these closed form formulas. These aren't the expanded formulas like we did above. These are the closed form formulas, so they give you the actual answer. So for instance, if I wanted to know the sum of the first 100 numbers, it would be 100 times 100 plus 1 all divided by 2. So I could actually plug in the numbers here and get the answer without having to add up 1 plus 2 plus 3 plus 4 plus 5 all the way up to 100. Same thing here. If I wanted to know what is the sum of the first 20 numbers squared, rather than doing 1 squared plus 2 squared plus 3 squared all the way up to 20 squared, I could just do 20 times 20 plus 1 times 2 times 20 plus 1 all divided by 6. So I could plug these into the closed form formulas and get the actual summation, the actual answer, very, very quickly. So we're going to refer to these numerous times. I need you to write those down. I need you to memorize these. We are going to be using these many times. And if you want to know about the sum of the first 100 integers, you can look at it. It was Carl Friedrich Gauss was the guy's name, the kid's name. It wasn't even a guy. He was a young child when he did this. And this is the one who realized so quickly that you could sum the first 100 numbers very, very, very quickly and easily. A very clever man. So I highly, highly encourage you to look that up.